Welcome back. In the last part of this section, we're going to introduce our second fundamental theorem of calculus. But before we get there, I have one little example I want us to look at that sort of sets the scene nicely. So here I've got myself a function, and this is a function, or an equation rather, that we would call an integral equation. We've already seen differential equations, so those were equations where we had one or more derivatives inside the equation. An integral equation, that's an equation where you've got one or more integrals in it. So here, y is this cos of theta d theta being integrated from pi over 4 to x. And as I said at the end of the last video, if I'm looking at a definite integral, it may or may not be something numerical. And in this case, it wouldn't be. When I integrate this, cosine of theta d theta, I'll find an antiderivative, then I'll evaluate it at x, and I'll evaluate it at pi over 4. Evaluating at pi over 4 will get me some sort of a number, but evaluating at x will get me a function in terms of x. So that means that this y that I'm looking at here should be some sort of function of x. And let's see that in action. I'm going to find an antiderivative, and for cosine of theta, the antiderivative that I'm going to choose would be sine of theta. So there we go. And we're going to evaluate that between pi over 4 and x. So when we evaluated x, we put in x and we get sine x. When we evaluate at pi over 4, we get sine of pi over 4. So I get sine of x minus root 2 over 2. So if I wanted to just sort of summarize what I've just figured out, I know that my function y is actually sine x minus root 2 over 2. The way we originally had our function y written was as an integral equation, but now we've solved that integral equation. We know that y is just sine of x minus root 2 over 2. So now the follow-up. Now that we know what y is, we can find the derivative of y if we wanted to. So let's do that. If y is sine of x, then dy dx is, well, the derivative of sine is cosine, and the derivative of root 2 over 2, well, that's just a constant, so that's nothing. So this is something that's kind of setting the scene for our fundamental theorem of calculus number 2. If you notice what I did here, I started off with taking a definite integral of cosine theta and then taking the derivative of that definite integral, which brought us back to cosine theta, or cosine x rather. Or in other words, integrating and then differentiating are opposites of each other. That's sort of the big part, or the big conclusion that we're gathering here. That's the fundamental theorem of calculus really in action. So for the fundamental theorem of calculus part 2, it's basically just sort of phrasing what we've just seen in action, which is if you've got a function, if it's continuous on an interval containing a, then if you're looking for whatever x you feel like that's in the interval you're talking about, if you take that function and integrate it from a to x, then take the derivative with respect to x, that's just getting f of x. And in fact, we saw that in the last example where we had our function going from pi over 4 to x of cosine theta. And when we did the derivative with respect to x of that, we got just cosine of x back. And that was our fundamental theorem of calculus actually going on behind the scenes. So the way that I've got this phrased, I have a function of t integrated with respect to t between a and x, and then derivative with respect to x. This doesn't necessarily need to be t. I mean, that was a perfect example that we just had. It was cosine theta and d theta. Just whatever interval, whatever variable you have here, it's going to be a different one necessarily than the one that you got on the integral itself. You know that if your function is continuous, then it's guaranteed by the fundamental theorem of calculus that there is some sort of an antiderivative, because you must have been able to find one to evaluate at x and evaluate at a. It's not guaranteeing that that antiderivative is going to be anything nice. So although an antiderivative theoretically exists, it might not be an elementary function. In other words, it might not be made out of a combination of sines and cosines and polynomials and roots and that kind of thing. It might actually be something much, much worse. And in fact, that's one of the things that you learn in calculus as you go further into your calculus journey. There are lots of functions that look relatively straightforward, that look relatively nice, where an antiderivative for that is really terrible and unfortunately difficult to find. Okay, so let's take a look and do some of these. The first one is straight up using the fundamental theorem of calculus part 2 as it originally stands. So number 1, we've got this function, t cubed minus 3t plus 1. It needs to be continuous on an open interval including 1, and it's a continuous everywhere, so we're good on that score, so I don't have to worry about that. And I'm integrating from some number up to x and then taking derivative with respect to x. So fundamental theorem of calculus number 2 says that that should give me just that function in terms of x's. That should give me x cubed minus 3x plus 1. That fundamental theorem of calculus tells me I don't even have to find the antiderivative and evaluate, because if I'm going to be doing that, then differentiating, I know that I'm just going to get my original function back. Now, sometimes things aren't quite set up in the place where you'd like them to be. So for this one, you'll notice the difference between the first example and the second. The first example had us integrating from a number up till x. And for the second example, we're integrating from x to some number. So I'm going to need to switch my limits of integration, actually, because the way that the theorem was phrased, fundamental theorem of calculus part 2, was that our constant was the bottom limit, not the top limit. So the 3 needs to be at the bottom and the x needs to be at the top. And that's not hard for us to do, because we had a theorem from earlier on in this chapter that said if you switch the order of the limits of integration, that just changes your integral from positive to negative. So instead of the sine of theta squared over theta minus 1, it'll be negative sine of theta squared over theta minus 1. Okay, I'm going to do one little bit here, and I'm actually going to do two things for the price of one. So 2 steps. Number 1, I know for an integral, constant multiples could be taken outside, and so I could really rephrase that as minus the definite integral of. I also know for derivatives that constant multiples could be taken outside, so I'm actually going to take that negative outside of all of that and say this is the negative of the derivative of the integral from 3 to x of sine of theta squared over theta minus 1. And now I have it ready to go. So I'm looking at this function, sine of theta squared over theta minus 1. The only discontinuity happens at 1. So 3, that's where we're starting at. That's definitely, there's an open interval around 3 where sine of theta squared over theta minus 1 would be continuous. We're integrating from 3 up to x and then differentiating with respect to x. So fundamental theorem of calculus number 2 says what I should get is this sine function just in terms of x. So I should get sine of x squared over x minus 1. And of course, I've still got that negative in front from before. So actually, I get negative of sine of x squared over x minus 1. Okay, so last one to look at for this fundamental theorem of calculus part 2 moment. I've got this function, and you'll notice this is even more complicated than before, because instead of just being from 0 to x or some number to x, we're now going from some number to some function of x. So I want to rephrase this in a way where I can use the fundamental theorem of calculus. And so I'm going to just make a little note here on the side. I'm going to say that u is the same thing as sine of x. I will make a note here, of course, u really is a function of x. So I'm going to have to keep track of that, because when I look at this f of x, that should be now really the integral from 0 to u of 1 over w squared plus 1 dw. We're looking to find f prime of x. So I want to find df dx. And I know if I'm thinking about chain rule tells me that if you wanted the derivative of f with respect to x, and we've got some sort of little intermediary function u of x in play, that's the derivative with respect to u times the derivative of u with respect to x. Now, just as a little side note, we have this function that's integrating from 0 to u, 1 over w squared plus 1 dw. And if I were thinking about that, that's my f. And if I wanted to take the derivative with respect to u of this integral, fundamental theorem of calculus would say, well, hold on. This function is continuous for all w, so it's definitely continuous around 0. We're going from 0 up to a variable u, and differentiating with respect to u. Fundamental theorem of calculus says that I should just get 1 over u squared plus 1 from that. So my derivative of f with respect to u should be 1 over u squared plus 1. Du dx, what's the derivative of u with respect to x? Well, u is sine of x, so the derivative of u should be the derivative of sine, which is cosine of x. And so now I'm just going to finish things off. I don't want to have two different variables mixed together. I don't want x's and u's together. So I'm going to go backwards and say, well, x was sine of u was sine of x. So we'll have cosine of x in the numerator. And instead of u squared plus 1, I'll have sine squared plus 1 in the denominator. And so there we go. We've now found f prime of x, that is cosine over sine squared plus 1. Okay, just a last couple of things to look at here. This last little theorem, the net change theorem. So if you're thinking about some sort of function that's a rate of change of f, then if you were to look at the definite integral of that rate of change, then that would be telling you what the total change is, or what the net change is for that function over that interval. So for this, if I'm thinking about this water tank that I'm looking at here, I have water as leaving a tank at a rate of 1,000 minus 60 liters per hour. So if V is the volume of my tank, then this 1,000 minus 60, that is the change in my volume with respect to time. That's what this 1,000 minus 60 is. That is my derivative. So what this is telling me is if I wanted to know how much water is leaked out during the first 5 hours, or in other words, I want to know what is the net change in my volume over 5 hours, the net change theorem says, well, the change in volume over 5 hours should be the integral of your rate of change from 0 to 5. So our change in the volume over those 5 hours is the integral of our rate of change from 0 to 5. And then all I need to do is to find an antiderivative and then evaluate, and then life is good. So away I go. I'll just find my antiderivative, and that's 1,000t minus 3t squared. And I'm going to evaluate that between 0 and 5. And when I do that, I get 4,925. So that means 4,925 liters have leaked out during the first 5 hours. So there we go. This is the total change from t equals 0 to t equals 5. According to the net change theorem, that would just be the integral of the rate of change from 0 to 5, which gave us 4,925 liters. And of course, we want to maybe ask the question about what happens during the next 5 hours. So how much water is leaked out between time equals 5 and time equals 10? Well, that would just be the definite integral from 5 to 10 of our rate of change. And then we would do the same thing as before, evaluate that definite integral. So we found an antiderivative, then evaluate at 10 and evaluate at 5. So evaluating at 10 gives me 9,700. Evaluating at 5 gives me 4,925. So during the next 5 hours, it looks like 4,775 liters are leaking out.